No, no.
Hey,
Hey,
well,
Ron.
hello there, astronomy freaks, cosmic kooks. We got another Astro Hour for you. It's through Zoom and it's on YouTube and all for educating the populace on behalf of the Santa Barbara Astronomical Unit. I'll be your host, at least getting into it, Ronnie Heron again, welcoming you to the SBAU Astro Hour, number 277. We're into the middle of our sixth year of being on the air. This is for the week of August 24th through the 30th, 2026. And we welcome you to our club. SBAU meets the first Friday of most months at the beautiful Santa Barbara Museum of Natural History. It's where we gather outdoors at night about a week later, second Saturday of every month, for our well attended star parties. You're also going to find us out there, the Astro Unit telescope set up at state beaches and hotels, schools, Westmont College this week, for example, and even the Camino Real Market, the shopping center. Get the whole story online, all right, at sbau.org. Here's this week's topics. Parts of the Earth were seeing last week's eclipse of the sun, and you know what? So was Mars. It had its own little, doesn't have as big of the moon as we did, so I'm not sure about their eclipse. NASA's Lunar Reconnaissance Orbiter caught that crash of Falcon 9. Moon's got a new crater. What was the first photograph ever taken of a solar eclipse? Well, try mid 19th century, 1851. Wait till you see the device used by Norman Lockyer to discover helium. Turns out Big Bad Betelgeuse has a companion. It's been married all these years. It's a binary. Congratulations. Any excuse to open a bottle of wine here. We'll also check out another binary system up in Corona Borealis this week, the Northern Crown. What's Messier 73? Well, it's an Aquarius, the water bearer. And Thursday, we're all going out to Westmont's Observatory for a partial eclipse of the moon. That'll be long before sundown. Come join us. Here's our crowd, our crew. Ladies and gentlemen, welcome the president who's in charge, Jerry Wilson, 10 years.
Good morning, everybody, and good morning, my sister Joyce and Calvin and Riley and my lovely wife, Pat.
Oh, bless. I know Pat's probably listening. Do you think the rest of the gang is?
No, Pat's out shopping today. She took the car and left.
Well, that's better than seeing the doctor. Thank you.
Yes, yes.
Longtime member and Captain Outreach. He's a force to be reckoned with. He's the best on the planet. Chuck
Oh,
McPartland.
good morning.
In the universe.
He's kind of a walking AI check mark. What do they call that? The checker person that fact checker. That's the word I was looking for. Pat McPartland is his wife. She's our incredible treasurer and merchandise manager. Former Westmont science professor Tom Whittemore edits our newsletter and has forever, and he's married to Maureen. And I'm going to call this a top-notch lensman. Tim Crawford is going to become one of our best speakers in December. Tim.
I'm good at scratching mirrors.
And his wife is Karen. You also said you had something you wanted to show me. How do I see it?
Oh no, I will share that another time. But it's a great picture of we have these little stuffed animals in the Broder Hall, and we stuck one behind a tester, an optical tester that we use to test mirrors, and it's a great little picture.
It's been in the newsletter, Tim.
Oh, okay. Yeah, it's great. The way I'm going to present it in December is that, the more eyes that test, the better off your optics are going to be because you get more eyes on it and it's good. And we even brought in some specialists, and I'm going to have a picture of that little whatever it was.
That'll be on your
Gopher or
talk.
squirrel.
This talk, ladies and gentlemen, is the three questions. You'll probably get more that you get asked at star parties when you set up in the dark. And,
A lot. Yeah.
Are you going to get a good pictures on Sunday? You guys that watch the sun at the
No, we get a lot of customers have been trying to get pictures through my eyepiece, and some lady yesterday actually got a pretty good little image, and it was good. But for some reason, the new iPhones having so many little lenses on them, just about the time they're going to snap a picture, the lens will switch. It's absolutely it's really maddening.
Well, I imagine you're looking for prominences and flares and little dark spots, sunspots, but sometimes there's not one there, is there?
No, we've been kind of a
That's
quiet sun, and
Yeah.
but the last couple of Sundays
Huh.
we got a couple of little prominences, and there were some sunspots that were capable of some X-class flares, and those are the ones that really can knock out a lot of electricity if they are aimed right at you.
well, you'll have a whole half hour on half of a whole hour on December. You might want to work in some of that Sunday viewing along with your star party Saturday night. Ladies and gentlemen, President Jerry forwards us silly science cartoons, at least half a dozen. I think we got 7 this week. And here they come and get our show started here, number 277, with some humor, some pause. You're going to have to increase the size of that sucker. Who wants to take this one on, Chuck?
Two ladies, a couple and a lady talking to each other, and one lady says the other, George is an astronomer, and he's looking straight up.
Right up out of the code, okay. That's not Larson, is it?
That's
Oh,
Herman.
No, it's
No.
Herman.
All right, you're going to have to describe this one, Mr. President.
Oil tanker slips anonymously through the Strait of Hormuz by adding a fake nose and mustache.
Works every time. The Iranians never see
You
it.
remember these glasses? They used to go around in the 60s and 70s. Are real popular.
Yeah.
What are they called?
Groucho Marx.
Yeah.
Groucho glasses.
Oh, they come with the nose and
And the bushy
okay.
mustache.
Tim Crawford, what's going on? We're having a close encounter. A couple of astronauts on another planet.
Yeah, it looks like I missed these. Let me see. It said, "No, Jim, this could not have been an email." And
And
In
down
other
here it
words,
says my inbox is astronomically full as it is.
oh, I see it. The left side, the meeting. Who does the meeting? You know the name of this cartoons?
Um,
Rhymes with
It's
orange.
called Rhymes with Orange. Yeah.
yeah. Comic Kingdom.com rhymes
Not,
with
nothing
I don't
rhymes
see
with orange, I heard.
I don't see a oh, there it is. Hillary B. Price and Piccolo.
Okay. Couldn't have been an email. And that's some meaning to me, I got to tell you.
Italian for
Okay, Tom Whittemore, you want to walk us through what we're seeing here?
I'll try. Let's see. I spent billions building this spaceship. Now you must admit that the Earth is not flat. No, that's
Flat.
probably just a painted backdrop.
That's right.
The main
Flat
reason,
Earthers.
yeah, main reason people pay for space tourism.
They don't believe the Earth is round.
Yeah. Yeah, no, there's still
All
those.
right. I think President Jerry's going to have to walk us through the bubble heads, talking
XKCD.
stick figures. Yeah, they're talking.
I'm sad that we missed the Perseids. Well, there's still the Geminids. Yeah, but they're in December. The Perseids happen when it's warm enough to lie outside with a blanket, and we found a good mosquito-free beach. So we just lie around watching the stars and eating snacks. One year we saw the aurora. You know, I think I heard that the Perseids might be late this year. Yeah, actually, I heard that too. Later, seems like a normal number of meteors. Guess I heard wrong. Maybe the Perseids are next week. Oh, good thinking. Let's come back then, just in case. They're just guessing it when
It's just an excuse to go to the beach.
yeah.
Oh, this is the one I wanted Tom Whittemore to do because it's got a pun. He's our resident punster. Can you read it? We're looking
Yeah,
at
I can see it. We did it. We hit the edge of the universe. Yeah. Aren't you excited? Yeah, it's just, there's nothing to look forward to. You dedicated your entire life to a pun? Yeah, but that's all behind me now.
made it to the edge. Okay. Okay, Chuck? Off the mark.
Okay. This is kind of just a visual one, but there's a lady walking a dog and a fellow walking along with a briefcase, and they're looking at this fellow in between them that's got little feet sticking out of his shoes, and he's walking along, and it says, in addition to self-driving cars, Google is also working on self-walking shoes.
There you go. That's where AI does them good. I'm ready for that.
Yeah,
Mark.
everything is an AI, Ronnie.
What that reminds me of is when we were kids, we had these bicycles that were super heavy, and you had to, if you wanted to go like pedal up to the mission, it was a workout. But now
Huh.
you see kids on these electric bikes all
Yeah.
over the place. Man, it's easy.
Yeah.
Are we gonna end up with no muscles at all?
That's for some of them, they're going to end up with fat rear ends and skinny legs.
Yeah.
You
Have you seen Wally?
Yeah,
you remember,
Wally. Wally's a good movie to exemplify that.
yeah.
Okay,
This the Mars. This is Mars's eclipse.
you can see this?
Yep.
Yes.
Okay. This is a total eclipse of the sun from Mars, and it's the best they could do. Their moon, this is the larger of the two moon. What is that, Phobos?
Mhm.
And this is it in front of the sun. It's the best they could do.
Yeah.
No
Not
prominence.
only are they smaller, but they're much closer, aren't they, to the planet?
They
yeah.
are much closer, yes.
So that's only about what, several hundred yards across, or
13 miles.
few miles across. And it's the larger of the two. Deimos is a little smaller potato.
Yeah, like 7 miles across.
Hmm.
And Phobos is actually in a decaying orbit. So,
And this is taken from Perseverance.
Yes.
Glad it's still working.
Now this is a hard to see thing, but it's dark, so it's not washed out. This little blue dot is the Earth, and this is the moon Phobos occulting the Earth.
Oh,
So
yeah,
as you
yeah.
go along, it's getting closer, it's getting closer. Here the Earth is behind Phobos. You may remember that in the night sky. And here it is, it's passed by the Earth.
In front of Phobos.
No, the
Yeah.
Phobos has passed in front of Earth
Mhm.
from
Yeah.
the point of view of Mars.
Mhm.
Oh.
So Perseverance is doing occultations.
That's right.
Wow, who would have thought? Has that ever happened before? You
So
think?
it's a crescent. I'm sure it happens all the time now.
Yeah.
This is a crescent Earth. So you're looking very close to where the sun is.
Crescent Phobos.
Yeah.
Oh, excuse me. Yes, crescent Phobos. You start talking about them in reverse order, and I picked up on it. Okay. Now, this is the area of Einstein crater on the edge of the moon. So here we are looking straight down at it from the Lunar Reconnaissance Orbiter. And this is what it looks like after the
Oh.
SpaceX second stage hit. So you get a fan-shaped thing here where there's nothing splattered out, but you get debris out here and out here. And so I would guess it's probably traveling this way when it hit. So this is, what is it, about 60 meters across, as I recall?
I think 60 feet across.
Oh, 60 feet? Okay.
Well, one less space junk around our Earth, I guess.
Yes, well, we're going to be having many more. This is not the first thing to hit the moon from us.
They used to deliberately crash upper stages into the moon so that they could take measurements of the inside with the seismometers.
Yeah.
Huh.
This is the first photograph. I don't know if it's a photograph. It's a daguerreotype taken of the total eclipse of the sun in 1851.
Norman Lockyer.
What's that?
No.
Well, this isn't that he was the helium discovery. Who took the
Yeah,
picture?
that was a different story. This was much later. This is just a cool photograph that I saw, and it is good enough that you can see some Bailey's beads around here, and you can see a prominence there, and you can see a prominence there. It's quite a good picture. The eclipse was, I believe it was 80 seconds long, and that's what they used for the exposure of this. That is, when the eclipse started its totality, they took the lens cap off and exposed this for 80 seconds. Remember, daguerreotypes were not very efficient at absorbing light. It's a sheet of silver with photochemicals, a thin layer of photochemicals on it, and then it's treated once it's exposed to produce an image on the plate.
How accurate were they back then as to the full eclipse trail, the track across
You
the
mean,
Earth?
how were they at predicting eclipses?
No, how were they at predicting full eclipse? Did they know where to go to get
Yes,
a full?
they did. They would send expeditions around because different things, especially the transit of Venus, would give information about how big our orbit is.
Edmund Halley was predicting eclipse paths.
Yeah.
Really?
There was a lot of uncertainty in how wide it was going to be, but they could tell in general where the center line was going to be.
But I imagine a big part of the Earth back then got partial eclipses most everywhere. Only part of the sun.
No.
Well, doesn't it make a path across the Earth every time?
Yes, but the partiality isn't that wide a path either.
It's on both sides, I think.
Yeah.
Hmm.
Yeah, they always got the same amount of solar eclipses that we did. They come in cycles called Saroses or Saros.
Saros cycles, yeah.
Yes. So and they learned about that pretty early on based on empirical observations. Ancient people had pretty good understandings of the motions of the sky, of what you would observe. The reason for it and the shape of orbits was in dispute for a long time. They liked
Any of you remember when we had a full eclipse here?
Yeah.
I don't remember a full eclipse here. We had a very close to one here.
You usually have to go somewhere.
Yeah. Okay. So we're now going to talk about the sun, and we're going to talk about the discovery of helium, which was discovered on the sun much later than 1851. And
That's
this
Norman Lockyer.
and what?
That's Norman Lockyer.
Yeah, now we're talking about Lockyer. Now, this is the spectral radiance of a black body, which is not generally understood what it is. How can a black body be so bright? But a black body is something that has an absorption coefficient of near unity, or actually at unity. And you make a black body, because these are useful instruments. You make a black body by taking a large sphere, not too large, say a foot in diameter or so, and you cover the interior with super black paint. And then you have a small hole in one side, and you look at the radiation that's bouncing around inside the black hole source. And you get distribution of radiation that is characterized by this. This is Planck's radiation law from about 1900. It shows the spectral radiance, that is the radiance coming out per wavelength. And for our sun, which is a 5,800 Kelvin black body, we would be right about here at 5,800. And that would be close to the 6,000 line. So the sun is right here in its output. And this is the peak output. And this is where our eyes have evolved to have the most color sensitivity, because that's the sun. And this spectrum to us defines white. All these things, I think Newton was the one that decided that white is all the colors combined together. Now, if you do that with paint, you get mud. So that's not what they mean. They mean light. But as you get down here, this is long wavelength. This is the ultraviolet out here. This is the center part, the yellow of sodium, the doublet, and red for hydrogen alpha is out here. And then at 800, you go into the near infrared. This is 1 micron. You're definitely in the infrared. And now these are different infrared wavelengths. Now, every temperature rise causes this peak to move up and to the left. So if it's hotter, the peak rises up here. The peak moving to the left is called Wien's radiation law. So this is what a black body looks like. And the sun is a black body emitter. The sun has no atoms in it. It has nuclei and electrons, but they're not bound. So this is the backdrop you see on the sun. And what you see, well, if you take a spectrum of the sun, you see this. This is a high resolution spectrum. And you see in the background, you see the colors, and these come from the surface of the sun, which is an emitter. But you see these lines here are in it. These lines are absorption. And as soon as the nuclei and electrons get out of the sun's surface and they form the atmosphere of the sun, they find each other, they fall in love, and they get together and they become an atom. And now that defines energy levels. And so when an atom is at an energy level and it finds a radiation that it likes, it absorbs that radiation and gets excited to a higher energy level. That absorption process is these black lines. So the black lines are due to the atoms in the atmosphere of the sun and not due to the sun's body itself. So what this guy Lockyer did was he looked at, rather than get confused with the prominences, he wanted to look for emission lines on the sun. So that you don't see emission lines on the body of the sun, but if you look off to the side and you look at prominences, you can see emission lines because the prominences are above the surface of the sun. And so you can get emission lines. And they were looking at these and studying them, and they found two lines that were out here in the yellow part. And I meant to look up which ones they were on an absorption diagram, but I didn't do that. So they're out in this region, in this band here somewhere. There's two lines that they couldn't match up with any chemicals they knew on Earth. And they finally discovered that chemical on Earth in a lava bed of gases released in a lava bed. And they named that element helium because helios means the sun, and it was discovered on the sun. Any questions so far?
Are the two brighter black lines in the yellow band, is that, or could it be them?
That's
It
the
could be.
sodium.
Yeah, that's right. These are the doublet of sodium. If you put salt, which is sodium and chloride, if you throw it in your fireplace or campfire overnight, you can see a burst of a yellow flame. That's the sodium. And this humongous thing up here is the hydrogen alpha light for hydrogen. A lot of hydrogen on the sun. I was thinking it's probably somewhere, let's see, I was thinking somewhere down here maybe, but that's just a speculation.
And you can see they're fuzzy on the edge.
Yes.
The two dark sodium lines are fuzzy on the edge. And that was a mystery for a while, but that's from the magnetic field of the sun.
Huh.
Yeah, fuzziness on the edge also is due to heat. So you get a little Doppler effect.
Right.
Light around here is motion of the atom in the magnetic field. And also the magnetic field. The sun has an extremely strong magnetic field. And I know that when you look at sun, people tend to think of it as a ball of flame. But a better way to conceive it physically is that it's a ball of magnetic field. And it's got all this plasma trapped in it.
Jerry, if those are sodium lines in the yellow and hydrogen is up there up above, then helium would be a simpler than sodium, so it should be to the right of that on the yellow band, wouldn't you think?
No, these atoms, for example, helium is very simple. It's a hydrogen, it's a nucleus and an electron. And yet you have bounces between multiple bands. You have, this is for hydrogen, this is part of the Balmer series. Then down here is the, what's the one that goes into the ultraviolet? The Lyman series.
Lyman.
Yeah, and then the Balmer, Lyman, and there's a whole bunch. As a matter of fact, people caught the pattern of that around the late 1800s. and different people were looking in different parts of the spectrum so they could get a new series named after themselves. And several graduate students, Pashan and someone else, got series named after themselves, and they were consciously looking for them to extend the pattern.
Right. I think one was the Pfunt series, Pfund, Pfunt. Right, Jerry?
Yeah, it could be. I've forgotten names. There are four or five
German
of them.
word for pound.
Yeah.
Yeah.
Oh, yeah, that's
Tim,
right. PF, yeah.
Pfund.
Yeah.
Tim, just because hydrogen is simple doesn't mean it has only the one line.
Yeah.
Yeah. And if those are the two sodium D lines, they're really easy to separate in a modest spectrometer. They're very
Yes.
easy to separate.
You know, not to, I don't want to slow it down, but to me, black body radiation or black body
Yeah.
is just, I just don't get it.
Okay. The
And,
black
and
body refers to the absorption. If you think of a surface, it has a couple of key properties. It has its absorptivity, that is what percentage of the incident light it will absorb, and a black body is at 1. It's a theoretical thing. There's no actual black body, but some of it gets close. We used to have a paint we used in industry called Cadillac Black, and it
yeah,
was the blackest black that you could get. Now I understand there's another thing that's blacker than black, blacker than cat. Okay, anyway, I'm not going to go there. But the absorptivity is how much they're going to absorb. Well, it turns out you have absorption, reflection, and emission. And so if you have no reflection, the surface is completely black, there's no reflection, then the absorptivity is equal to the emissivity.
Yeah.
So it will absorb everything, and if you heat it up consistent with its temperature, it will emit everything.
Yeah, and Tim, if you want to see the Planck radiation equation, get ready for a sleepless night.
oh. Well, I've never understood this, and I hope someday that we can, Tom, you and I can sit down and go over it, because I guess where I get stuck is that it's not the sun absorbing this. It's when it's the radiation that's being absorbed by a spectrometer.
Yes. So, Tim,
No.
if you look at the sun, deeper into its atmosphere, it's sitting there glowing, okay, like Jerry says, like a black body, but it gives out a continuous spectrum. So you look at these colors here from the red all the way down to the blue. That's all continuous output, right? And like Jerry said, once you get a little bit outside of that, now you're starting to see absorption for certain chemicals that are actually in that atmosphere. Okay. And I'm pretty sure that those two, Jerry, are the sodium D lines, and I see a lot of Doppler shifting from motion, like you said.
Yeah.
Yeah.
And Tim, the absorption lines are when you're looking for something that's cool in front of something hotter.
That's exactly it.
That
Thanks,
way.
Chuck. That's it.
And and the emission is when you're looking for something hot. What elements are there that are heated up?
Right.
Uh-oh.
And those appear to be bright single lines, Tim.
Yeah.
You're looking for something cool that's in front of something hot.
Yeah.
Yeah.
Exactly.
So if you heated up a bunch of sodium, you'd just get the yellow light,
Right.
primarily
Mm-hmm.
in the visible spectrum. You'd also get other stuff, but
Mm-hmm.
And that's what's so cool about spectrometry lab in high school. You have all these gas tubes sitting there with all these different colors, and you're looking at them through
Yeah.
prisms and stuff. But what they're alluding to is that if you want to see these black lines as bright lines with no bright background,
Mm-hmm.
off the sun, you look at a prominence, and then the prominence is in the solar atmosphere, and it's emitting. So you will see these black lines as bright yellow lines with no background if you look at a prominence.
Huh.
Hey, Tim, if you look down towards that blue, look at
Uh-huh.
how complex that absorption spectrum is.
Yes.
And my feeling is you're seeing quite a few of the cadmium K lines and things like that.
Yeah.
That when you're looking down in there.
Now, when people are using this, may be not
I'm sorry,
related.
calcium, not cadmium.
The calcium K
Calcium
filter.
K line, yeah. We used to image in calcium K the sun when I worked at the labs.
And
Yeah.
then what I understand is that the hydrogen alpha that we use and the calcium K that they also make, it's a different layer of the sun that they're
Yeah,
looking
this is
into.
the atmosphere, And
Yeah.
the color is from the ball of the sun. It's from the sun.
Exactly. That's it. That's it, Tim. That's the whole mystery solved.
Yeah.
Okay.
Can I just
But-
throw in my stupid question real quick?
Tim, if you didn't have anything, cool in front of this thing, it would be this wonderful blend of colors that you're
Yeah.
seeing there. Okay. Go ahead, Ronnie.
Oh, I was just wondering, at the time he discovered helium, which is number 2,
Mm-hmm.
we knew hydrogen. Did he know the higher elements, carbon-6 and oxygen-8, and were they already known?
We knew the spectra for elements that we could easily mess with in the lab.
In the
under
laboratory.
temperatures and
Yeah.
pressures.
Mm-hmm.
But nobody ever had the helium.
Well, helium is really hard to catch and find.
Yeah.
Helium turns out
where do we get it on the Earth?
we get it as a byproduct from natural gas wells.
Yes, yeah. A lot of it comes from Texas and also
Really?
Russia.
And
Yeah.
Minnesota now too.
Okay.
Jerry, could we sometime take on the subject of how to, a spectrometer, how they actually came up with this and how they make them? And
All right, you're my
sure.
shill today.
Yeah,
Well, it's just Newton, just a prism will do it,
right.
or a CD-ROM.
Right. So here is hydrogen. There's helium, an inert gas. It needs 2 electrons. It's got to. It's hard to react with things. And it escapes overnight from rubber balloons. Small molecule, and it gets out of everything.
that's the one that they're having trouble with in the rocket ships, right?
Yeah.
Yes.
Okay.
Okay, this is a spectrometer.
Oh,
And
wow.
this is a photograph.
Beautiful. That thing's so beautiful.
This is a
Lockyear's instrument.
This is Lockyer's spectrometer.
Mm-hmm.
Yeah.
And I noticed somebody dropped it or something because one of the prisms is kind of chunked up
Mm-hmm.
in one of
In
your
here?
other photos. In one of your other images,
Oh,
you can
okay.
see
And Ron, do you know the definition of a prism? It's where they
coming to be real.
it's where they keep criminals.
Why I give you the puns, what a more.
Tim knew that one.
Yeah, it's always good every time.
Okay, this is the input. This sticks in the eyepiece tube of your telescope. And it has a slit in here. And the slit takes collimated light. So you want light that's parallel. It does not come to a focus in this. So it's called an afocal system. So it's just a beam of parallel light. It goes down here. It hits the first prism and it bends this way. And then it hits the next one. It gets bent more, and the glass spreads out the spectrum of the light. And to do this much around here, you need 1, 2, 3, 4, 5. Well, this one should be lined up, but anyway, you go through a number of prisms. It gets the spectrum wide as you need, and it gets it fainter. So this can be a challenge because everything was visual at that time in the 1800s. And then in here, there's an eyepiece, and this focuses the light so you can see the lines.
That's
This is,
amazing.
Yeah,
That's-
one of them. Yeah, this one back here got dropped.
Yeah.
Are they made of glass or crystal?
They're made of glass.
I'll be damned. So melted sand.
So Ron, at Purdue, where I went to school, I took a spectroscopy course late, like on my senior year. And the spectrum that we had was old world stuff, sort of like this, okay, with prisms splitting the elements light. And the thing was so broad, they had a special room that you could see the spectrum for different kinds of elements just spread on a big room. Imagine, like 20 meters. I mean, really big. So you can see incredible detail.
Any criminals in there?
Yeah.
And
But it was
everybody
really,
went out
really
and
good lab. It really is advanced spectroscopy. Just one of my favorite ones at Purdue.
It is absolutely fascinating.
Yeah.
How in the
How
hell
many
did
of
they
you saw
come
that,
up with this?
that Pink Floyd album that had a cover,
Yeah, Dark Side of the Moon.
Dark Side of the Moon? I wonder how many people
Floyd?
triggered into science from that.
So anyway, this is we won't get into that today, but the reason that prisms spread out the spectrum of light is because when light enters a prism, the speed of light is different in the prism than it is in air.
Right.
And it's
Uh-oh.
different for different wavelengths.
That's
Yeah,
right.
and
Uh-oh.
that's the meaning of dispersion. It's different for
Right.
different wavelengths.
Right. The index of refraction is a function of the wavelength.
Yeah.
Yeah.
So
Yeah.
if light travels at a constant speed of c, how come it has a different speed in glass? So that's a nightmare for another talk show.
Good, good, good. I love it. I love it.
Okay. This is a picture of someone, maybe Lockyer, using this type of spectrometer. Here he is looking through the eyepiece part, focusing. And these things, there's a lot of extraneous parts here. That looks like a finder scope. Light goes in there, goes around there, and comes out here.
Sounds like
a
music
famous song
from
in
the
the
Five
30s.
Pennies.
What's that?
Sounds like music from the Five Pennies.
Yeah. You press the first valve down.
Yeah, yeah.
Goes
Music goes round and round.
Well,
Well, this all evolved from Newton, didn't it? When Newton had that prism in front of the window.
yes. He's the guy that started it all. You got him to blame.
Yeah, and then
And Bunsen-
Herschel discovered, Tim, that there was a part of the spectrum you couldn't see, but it still had heat.
Yeah.
He was the guy. That was Herschel.
Discovered infrared.
John
That's it.
or
No, William.
William, the dad.
yep.
Billy.
I always get them mixed up.
Yeah, and people, saw that when you burn things, your Bunsen burners came about because they had a very, I don't know, I guess a spectrum you could easily subtract. So that when you burned elements in the lab, you could get a pure spectrum of what element you were putting in, like sodium.
Mhm.
Yeah, Tom, you probably know more
Yeah.
what the Bunsen background would be.
Yeah. I can't remember the details, but
Yeah.
I always thought
I always remember seeing those sodium D lines easily split
Yeah.
at Purdue. It was really neat. Yeah. We did that at Westmont too for the kids, the students. Mike had some pretty good little spectrometers that he let us bum, from his advanced lab.
It's amazing that we get, this is another question I get out there a lot, is that how do you know what the stars are made of? And I said, well, they're
Yeah.
using a spectrometer. And whoever invented this, was it that Lockyer guy?
No.
Yeah.
No.
Yeah, the greatest story, Tim, is this was going on in the 1850s, late 40s. And there was a French philosopher, Lecomte, who said that we'll never know anything about the stars. They're too far away. Then spectroscopy was
Yeah. He said all we have is their starlight, and that tells us.
Yeah, we'll never know what they're made of because they're too far away. And then
Well,
spectroscopy just stomped on him.
it's a question I get out in the field a lot. And that when I answer and say they're using spectroscopy to look at the lines that it produces, they just don't believe me. They just say, you just can't do that. And I said, no.
Well, it's the electron shell configuration of whatever you're looking at.
Mhm.
But you have to have those elements in the lab to confirm it.
Yeah.
Right.
Well, now you can, it's also dependent on temperature and pressure. So now you can calculate some of that just from quantum mechanics.
Right.
Oh, wow.
When
And
I-
then you'll have gas tubes, neon, mercury, things like that. They have beautiful, unique spectra that you can see with these instruments very easily.
Well, I vote for more of this, Jerry.
Well, when I was doing SpectroLab back in the 60s, we
Mhm.
would take an image of the spectra of what we were looking at, and there was it was like a bifocal glasses, and at the bottom of your film we were putting on a spectra of a known source, like
Yeah.
sodium. And so then on the same piece of negative, you could see the lines you were trying to figure out, and you could see the sodium lines, so you could calculate the exact wavelength of the lines you were after, and you could get the energy, and then you could go track down what it was.
Yeah.
And you could also, if it was shifted relative to the reference, you could tell it was moving.
Mhm.
Oh, okay. So there's your red and blue shift, huh?
That's
Yeah.
it. All right. So here now we're going to change topics. Now we're going to
Oh
look at
man, I'm
this is
bummed. Hey,
this
Jerry, I vote for more of that stuff.
this is an image of Betelgeuse,
Mhm.
the star up here and the shoulder of Orion.
Yeah.
By the way, this is a nice picture of the
Yeah.
Barnard's Loop.
Barnard's Loop.
Barnard's Loop. Thank you.
North
And
Node.
this is using adaptive optics to subtract out the main star Betelgeuse and just show its companion here. Now,
Oh,
the companion of Betelgeuse is actually in the atmosphere
yeah.
of Betelgeuse itself. And this is an artist's concept of what that would look like. There's still a well-defined surface for a photosphere for Betelgeuse, but it's very leaky. So this star, its companion, Betelgeuse B, leaves a trail.
Mhm.
So
What kind of trail?
this kind of trail.
Awake.
Yeah, wake.
Oh, okay. Okay.
Whatever this is emitting, this is its solar wind
Oh,
being
okay.
blown behind it as it passes through the debris from
Okay.
Betelgeuse.
So it's probably plasma, huh?
Yeah, oh yeah, definitely.
No, it's a star, it's not a planet.
It's a star.
Star.
Star's not a star has to have fusion going on in its core to be a star.
Mhm.
How would it compare in size to ours?
To our sun,
Yeah, is it a red
I
dwarf?
believe that the
No.
companion to Betelgeuse is smaller than our sun.
Well, it may be a red dwarf orbiting a
No,
giant
no.
red.
They're saying in your article, it says it's a blue-white A or B type pre-main sequence star. So it
Yeah.
hasn't started hydrogen fusion yet,
Okay, good
still
point.
collapsing,
Yeah.
but it's hotter.
And it's got enough mass that they're giving it a pass on being a star.
1.5 the mass of the sun.
Yeah.
Mhm.
And it's not
So,
in brown dwarf stage.
No,
no.
it's too massive for
Definitely, it
that. It's
hasn't
collapsing
started.
down to form a fusion
Yeah.
star, but it hasn't reached that point yet.
So, what is a star that's in that condition doing? Is it fission?
No, it's just heat from the gravitational collapse,
And
from
yet it's
compression.
emitting light and it's got energy leaving it and it looks like
Yes,
a
it's
star?
brighter than it will be when it finally
Yeah.
starts doing fusion.
For example,
Oh, wow.
Jupiter, Jupiter is heating up because of its own contraction, and it's emitting more radiation in the infrared band than it's receiving from the sun.
Wow.
Okay, we're
Amazing.
moving on now to something that I spent a lot of time trying to find out an answer that confuses everybody. So we have to accept that. This is a Zeta Corona Borealis. It's right here. There's the famous crown, and over here is Zeta. Zeta is a fifth magnitude star, and it's part of a double star, Zeta Corona Borealis. This is an amateur's drawing of it from 2007, 6-inch f8 Newtonian. So 10 millimeter Sirius Plossl, that's a medium high power for that scope. So it's easily within the range of what we use in our outreach to see. So this is what it looks like, a blue and a blue and a yellow star. And it turns out one of these two stars, it's a double, but one of these two is a quadruple star. That is, it's 4 components. And they can tell that because of the spectroscopic behavior of the lines in it. There are repetitive lines, they're offset from each other, and their relative position from each other moves and in time, but they cannot resolve it to see it. And so they are trying to, many graduate students are spending their lives trying to figure out what the exact configuration of this star is. They're looking at it primarily, I guess now the consensus is that it's 4 stars in 2 sets of 2 all in the same plane of the orbit. There are other configurations that are possible, but they're settling on this one to do it. So this is, if you want to get in the action and get a PhD in astrophysics, get your spectroscope out there, take the spectra and solve it mathematically.
Two sets of binaries interfering with each other or orbiting within each other's orbits. Same plane, is that what you're saying?
Yes.
Four
What?
stars.
There's in one of these, there's four. The other one is just one star. And
Yeah,
together,
I
the
understand.
one and the four are a binary system.
And the spectrograph is the key to the whole thing.
Yep.
Wow.
So
10
this
millimeter
is
fossil. Wow.
this
The
is the
2x
HR.
Barlow too.
Yeah, he doubled it, Tim. Do you see
Oh,
that?
okay.
240X from 120. Yeah.
So these are the two stars of Zeta Corona Borealis. This is the one that is four stars, and this is the one that's one star.
Mm, mm,
So
mm.
they are on the main sequence.
Mm-hmm.
And they're
they're
both
totally
really
different.
blue.
Yeah.
So these four stars here are assumed to be the same composition. That is, they're the same type of star.
Yeah.
So they're about equal mass.
And Ron, that vertical axis is not their actual brightness. It's their brightness at 10 parsecs. See that? That's the absolute magnitude, MV.
There's a pretty good idea that there's probably no exoplanets in that system.
Yeah.
The
Oh,
hell
if
with
there are
the night-
exoplanets in there, you'd get quite a show.
I guess.
Yeah, if those are actual magnitudes, Ron, they'd be bright.
Yeah.
Why are there so many dots?
Those are other stars.
Those are other stars that, make up this complex.
Oh, I see.
It allows you to draw the Hertzberg-Russell line through there. And
they're
those stars
different
have moved away. See, they've moved away from they've evolved off the ZAMs, the zero age main sequence.
So this is a rare phenomenon we're looking at. There's not a lot of this up in the sky, right?
Yeah, Tom, but the M sub V is absolute magnitude.
Yeah. So that's how bright they would be if they were only about 32 light years from us.
Okay.
Okay. But they're a heck of a lot further.
Okay, moving along.
Mhm.
This is the sky tomorrow night at 10 o'clock.
Okay.
The moon is down here in Capricornus.
Mhm.
And there is two Messier objects over here, M72 and M73, which is a puzzle because these are star clusters.
Mhm.
M74, 72 only has four stars in the cluster. And this one's a nice globular.
Yeah, it's a nice one.
Yeah. So this is a picture again. This shows M73. And then it also shows M74 too, which is these four stars right here. There. 1, 2, 3, 4.
Good grief.
So
I never knew that it was that.
why Messier picked those things? He must have had it depended. These were all he worked visually.
Yeah.
And this might be a night after a party or something, but his telescope might not be that good. And maybe there's, I don't know, cloud there or something. And he thought, well, these are just the brightest four. There must be something there. And he can't see it too well. So he named it M72, excuse me.
Well, I always thought that Messier was trying to tell other astronomers the objects in this list weren't comets. So maybe this looked fuzzy.
Right. But some of these were just compiled from when they saw them in his logbook. So even if he just mentioned it, sometimes it got in there.
Yeah.
Uh-huh.
Plus, he started later on padding his catalog to try to get elected to the Academy of Sciences.
I don't understand how some of the objects, as wild as they are, could be misconstrued as a comet, like Orion Nebula.
Right.
So, yeah, Tim, it's because beaucoup de vin. You're a lot of wine.
Yeah.
Oh, yeah.
Yeah, M40 is one of those, you know,
Mhm.
just a pair of stars.
It's a double star, yeah, two stars, yeah.
That's
Look
a
at
Oh,
that.
wow.
And
That's,
there's M72 or M73, the other one.
yeah, that's a really nice globular.
Yeah. And it's in a rich region of there are a
Mhm.
lot of stars and stuff,
In
structure up
it, in an eyepiece, it would be very small, though, wouldn't it?
here.
In
Yeah.
Mention the size.
Well, I'm just thinking magnitude, the collected magnitude. I don't know, 8, maybe. I don't know.
Hmm.
I mean, in an 8-inch refractor reflector like mine,
Oh,
it
you'll
would,
get it. You'll get it.
okay.
Yeah, it's a messy
Yeah.
object. You'll get it.
Hmm.
Yeah.
How many stars do they think's in that cluster?
The globular.
The
Yeah.
one we're looking at.
Hundreds of thousands.
Yes, hundreds of thousands.
This picture was made by an 8-inch f2 amateur telescope.
Wow, it's a wide field.
Boy.
There's a later picture that shows it pretty well framed, and it says it's 3.4 arc minutes.
Okay.
Okay.
Yeah, that's fairly small. That's down there around Ring Nebula size. So this is a picture of the 72 showing its distinctive 4 stars with neighboring stars that are not part of the cluster.
It's labeled 73, though.
Yeah.
Oh
that's
yeah,
a-
well this is M73. The labels are right. I'm just
No,
remembering.
this is M72.
Is it?
Yeah.
Yeah.
Huh.
You made it. Check
What did I
it out.
know?
73 is the globular.
Mhm.
Okay.
Okay, I guess I got the labels backwards.
Okay.
Wow.
Yeah, says it's 3.4 arc minutes in diameter.
Okay.
Yeah.
Oh no, M72 is the globular. You're right.
Okay. And doesn't say what telescope was taken to make this, but it looks like a large scope.
Hubble.
Hubble?
Yep.
Oh
Oh,
yeah, got it down
okay.
there as Hubble.
Okay.
Okay. Now,
Well, before you go, you just showed us 4 stars and called them a cluster a while ago.
that was a cluster. It's a very exclusive cluster.
Yeah.
What's the difference between that and a 4-star system? Not a binary or a
They're not
trinary, but
orbiting each other.
Right.
oh, they're not?
No.
But
These
they're
are
clustered
gravitationally
together.
bound or moving together.
Okay.
Now, it turns out we're going to have a partial eclipse of the moon, and it's going to be like this. The one edge of the moon will not be visible. This is obviously not a picture of this week's moon eclipse of the moon.
That'll
So
be
this,
Thursday, late in the afternoon, right?
yeah, this
Well-
is Thursday at 7:30 p.m. That's when the
Right.
moon rises,
Right.
located in Aquarius. And
Okay,
it will
early
be,
evening.
yeah, it will be an eclipse when it rises
Mm-hmm.
for us.
And it's going to be an
Peak is at like
Aquarius.
9:13.
Yeah, it's going to be an Aquarius, Ron.
If our
So it's going
shadow
to be pretty
goes on
low.
the
It's going to be
moon,
pretty low because of Aquarius.
well, that would mean it's as full as it can get, right? If our shadow is right on it.
Yeah, it's full moon. That's the Earth's penumbra and umbra there. So this is the interior dark shadow, and this actually isn't bright. This is the secondary shadow outside of the dark shadow.
And other than seeing just a larger version of it in Westmont Telescope, you're going to be able to see some features that are going to be invisible because of the shadow.
I don't think the Westmont telescope's going to look at this.
No,
Yeah.
It'll
binoculars
be too
are-
low.
Yeah.
You
Yeah,
can
I
see
get it.
features in this during eclipse. It's
Yeah.
not hidden. It's just dim.
Yeah. So Jerry, this reminds me of the first night I taught full-time at Ohlone College back in 97. I had a night class of students, physics students, and I knew there was an eclipse of the moon. So I took him out and I showed him that, and I had him calculate how big the shadow was covering the moon. It was really neat. It was really neat geometry problem. Really cool.
Yeah,
Huh.
good problem.
You'd like it, Tim. Geometry.
Yeah,
Mhm.
I don't like logs. They don't like me either.
Yeah.
Well, I thought
Trees,
logs would
logs.
be natural for you because the full term is logarithm.
Yeah.
Yeah, no, they just burn me. They burn my brain.
Is there any way to tie this in with the recent solar? Are we all in a long line?
Yeah, yeah. The line of nodes of the moon's orbit is lined up, so it's eclipse season. So you get a full, and then 2 weeks later you get you get a solar, and then 2 weeks later you on either side you get a lunar.
Mhm.
And the lunar will look the same everywhere on Earth, won't it? Unlike the sun.
If you can see it, yes.
If you can see it, yeah.
I didn't realize until I checked Sky and Tel this morning that it was a partial.
Yeah.
So it's what is it going to be about 90%?
Just like
96.
this.
Yeah,
It's going to be
it's pretty.
96% by coverage of the area of the moon,
Okay.
and
Okay.
some other 90% by percent of diameter of the moon that's covered.
Yeah.
There's two different measurements that are used.
Astronomy magazine says it will look just like this.
Yeah.
Okay.
That'd be my guess, Jerry.
Yeah.
It's
But
funny,
gentlemen,
but
if we had a full eclipse of the moon, would the Earth shadow cover it all, or would they be like a corona
It would cover it
at the
all.
edge?
We covered all.
Our shadow is really big compared to the size of the moon.
Right.
And thus, on the same scale, when it gets between us and the sun, so far right now it covers the whole sun if it's a full eclipse, right? But it's
Yep.
going away, and in years to come, we're not going to be covering the whole sun, are we?
Well, even now, when it's at the extremes of its orbit, it may not totally cover the sun, and you get an annular eclipse.
Yeah.
Mhm.
Is that what it's called?
Yeah, there was one of those fairly recently, right?
Yeah,
Yeah.
across the western U.S. Yeah.
Okay.
it's always I've taken a 4-inch refractor out to these things, and I'm convinced now that the best way to do this is with binoculars.
Mhm.
When you're looking through a telescope, you really don't see a lot of features on the moon. That it's kind of washed out. And I don't know why that is. It's red and or whatever color that eclipse is. But you get better contrast, I think, with binoculars than you do with the telescope.
Yeah.
Plus,
you-
yeah,
you
yeah,
get
because you
red-
get more of the surrounding sky, and you can see some stars. And
Yeah, it's
Yeah.
it's just better.
Yeah, and you get red, Tim, because the blue's been removed in scattering.
Oh,
you're
Yeah.
seeing the light from every sunset and sunrise around the Earth.
That's a
basically.
Ken Kilstrom. You stole that.
oh, how interesting. That's very interesting.
Yeah, Ken Kilstrom would always say that, Yeah. When we would show the kids, lunar eclipses out at Westmont.
So none of us are going to have our own scopes aimed at this sucker. We're going to Westmont, or is that where we set up?
They might have a couple of scopes, but really I'm telling you, Ronnie, the just looking at it visually, just by eye, is really good.
It's really pretty and spooky.
Yeah.
We're not going to see a clear edge to the Earth's shadow, are we? It's going to be this blurry blood moon.
Kind of like what you
fuzzy.
see here.
Yeah, okay.
Yeah.
There may be people on the Earth that don't even know what's going on.
Mm.
Haven't heard. Well, we reached the hour point, gentlemen. What does
Uh-oh.
the cat have to say, Chuck?
The cat is
Isn't it
saying it's
important?
time for snacks.
I think he's right. So let's all do. We hope to see everybody again next week, though, for program number 278 of the SBAU Astro Hour. Come join us at Westmont late Thursday, and then come to our meeting in a couple of weeks. We'll see you
Really-
next Monday morning, everybody. That's
Really
it for
nice,
today.
Jerry. Really nice.
Okay.
Okay,
See
thanks
you next week.
everybody.
Bye.
Take care, man. Appreciate it.